Welcome to today's Explainer. We've got a seriously amazing journey ahead of us. We're going to start with something you've probably seen a million times, like ripples on a pond. And we're going to shrink all the way down into the totally invisible, high-energy universe of the electromagnetic spectrum. We're talking about the hidden forces that make literally everything work. I mean, the sound of my voice right now, the Wi-Fi connecting your phone, the light from distant stars, it's all connected. Let's get into it.
Here's our game plan. We'll start with catching the wave, look at wave properties and behavior, tune into the science of sound, explore the electromagnetic spectrum, and wrap up with uses and dangers.
Okay, let's dive into this. Section 1, catching the wave. What exactly are waves?
You know, it's pretty tempting to look at a little toy duck bobbing in the water and think he's like surfing the wave all the way to shore. But actually, scratch that. That's not what's happening at all. Think about how he just bobs up and down in the exact same spot. That's because waves transfer energy, not matter. The wave itself is moving forward, sure, but the water particles and our little duck friend, they just vibrate vertically around a fixed position. So the energy travels, but the duck, he stays put.
And that brings us right to our first big category, transverse waves. This is exactly what that duck is experiencing. In a transverse wave, the disturbance is happening at a right angle, like completely perpendicular to the direction the wave is actually traveling. Think about tying a long rope to a doorknob and just flicking your end up and down really fast. The wave pulse shoots horizontally toward the door, right? But the rope itself is only moving up and down. That perpendicular motion, that's the absolute signature of a transverse wave.
But hey, not all waves do the rope thing. Our second category is the longitudinal wave. Now in this one, the disturbance is perfectly parallel to the wave's direction. Instead of going up and down, the particles are vibrating back and forth along the exact same path the energy is taking. It's kind of like a slinky if you push and pull it in a straight line. We're locking this definition in now because it is absolutely crucial for understanding how we hear things, which we're going to get to in just a sec.
Moving on to Section 2, Wave Properties and Behavior. The universal rules.
So the crucial point here is that every single wave out there follows one beautiful, surprisingly simple rule. V equals F times lambda. It's the universal wave equation. V is your wave speed, literally how fast the energy is cruising. F is frequency, which is just how many full waves happen every single second, measured in hertz. And that funky-looking Greek letter, lambda, that's wavelength, the actual physical distance between two peaks. So say a wave on a rope has a wavelength of 20 centimeters, and 3 peaks pass by every second. That's a frequency of 3 hertz. You just multiply them. 3 times 20 means that wave is traveling at 60 centimeters per second. It's the master equation that ties the whole wave universe together.
And since all waves share that math, they also share a few distinct behaviors when they interact with their environment. First up, reflection. This is simply a wave bouncing off something, like light bouncing off your bathroom mirror. Then there's refraction. This happens when a wave moves into a totally different material, like light going from the air into a swimming pool. It changes speed, which actually forces the wave to bend. Third is diffraction, which is when a wave spreads out as it bends around an obstacle. And finally, dispersion. This one is super cool. It's when waves, like white light, actually separate into their individual colors. It's exactly how a prism creates a rainbow.
All right, Section 3, the science of sound. Hearing the invisible. Sound is literally the perfect example of that longitudinal wave we talked about a minute ago. It moves through the air as a series of compressions where the air molecules are squished tightly together, and rarefactions where they're spread way apart. When you clap your hands, you're creating these rapid pressure changes that blast outwards. And hey, remember wave reflection? Well, when those longitudinal sound waves smack into a hard, solid surface, like a brick wall, those pressure waves bounce right back. The wall vibrates in sync and fires the wave back at you. That reflected sound wave, that is exactly what an echo is.
So how do our brains tell all these different sounds apart? It all comes right back to those wave properties. Pitch is directly linked to frequency. A super high-pitched noise like a dog whistle has a really high frequency and a tiny wavelength. A low-pitched rumble, like thunder, has a low frequency and a massive long wavelength. The volume, on the other hand, is all about the wave's amplitude, which is the height of the wave's peak. Big amplitude means loud. Small amplitude means quiet. So if your alarm clock has a high frequency and a giant amplitude, yeah, you're waking up with a serious headache.
Let's move to Section 4 and see how this builds. The electromagnetic spectrum, a continuous range.
Okay, we are officially leaving the world of mechanical waves, the ones that need water or air to move, and we are stepping into the massive, completely invisible universe of light and radiation. The electromagnetic spectrum is this huge continuous family of transverse waves. But unlike sound, these waves don't need a medium at all. They're these self-sustaining electric and magnetic fields that can travel right through the absolute vacuum of deep space. Just look at the sheer scale of this. From radio waves way over on the left, up through microwaves, infrared, visible light, ultraviolet, X-rays, all the way to gamma rays. And notice that tiny little rainbow sliver right in the middle? That's visible light. Literally all the colors our human eyes can process are just that one microscopic fraction of reality. The rest of this entire spectrum is totally invisible to us.
Now, keeping the exact order of this spectrum straight, from the longest, laziest wavelengths to the absolute shortest, is super important. So I've got a slightly ridiculous but incredibly effective memory trick for you. Raging Martians invaded Venus using X-ray guns. Radio, micro, infrared, visible, UV, X-ray, gamma. I know, it's goofy, but for sure you're going to remember it. Just keep in mind, radios are physically big objects, right? So they have the long wavelengths and low frequencies. Gamma rays shoot out of microscopic atoms, so they have teeny tiny wavelengths and wildly high frequencies.
And this brilliantly illustrates what is probably one of the most mind-bending facts in all of physics. Even though a giant radio wave and a tiny gamma ray seem completely different, all electromagnetic waves share some universal rules. They're all transverse, they all transfer energy, but here's the kicker. In a vacuum, every single one of them travels at the exact same speed, 3.0 times 10 to the power of 8 meters per second. That's 300,000 kilometers per second. The speed of light. So whether it's the Wi-Fi connecting your laptop or light traveling from a galaxy millions of light years away, they are all cruising through the universe at the exact same cosmic speed limit. No way around it.
Which brings us to Section 5, Uses and Dangers. The real-world impacts of EM waves. Now, what's really interesting about this is the direct critical link between a wave's frequency, its energy, and how dangerous it is to us. As you move up that spectrum to higher frequencies, the energy spikes. Now, radio and microwaves are fantastic for satellites and Wi-Fi because they cut right through the atmosphere. But intense microwaves can actually heat up water molecules inside living tissue. That's exactly why your microwave has that metal mesh on the door and why some folks use hands-free for heavy phone calls. A little higher up, UV light is super handy for checking security ink on money, but too much of it from the sun damages your surface cells, causing sunburns and increasing the risk of skin cancer. Then, at the absolute extreme end, we've got X-rays and gamma rays. Their waves are so tiny and packed with so much energy that they become highly ionizing. They slice right through soft tissue to show us broken bones. And gamma rays are even used to sterilize hospital equipment by literally obliterating bacteria. But that exact same ionizing power, it can mutate our DNA and cause severe cell damage. We use their incredible power, but we have to hide behind heavy lead shields to survive it.
So I want to leave you with a final thought to chew on today. Right now, as you're sitting there watching this explainer, you are submerged in a literal ocean of invisible waves. Wi-Fi signals, radio broadcasts, the infrared heat radiating off your own skin, even leftover cosmic radiation from the dawn of the universe. It is all bouncing, bending, and zipping straight through your room at 300,000 kilometers per second. Seriously, how much invisible energy do you think is passing directly through you at this exact second? It's kind of wild to think about, right? Well, I hope this explainer helped make the invisible just a little bit more visible for you. Thanks so much for joining me today. Keep asking questions, stay curious, and we'll catch you on the next one.